In this video, I want to show you how to complete the equilibrium lab that we're going to do in class. In the lab, what we're going to have as a situation is we'll have a meter stick suspended by a single string, and we're going to be told where to place one mass, and we want to figure out where to place a second mass in order to put things in equilibrium to balance them out. In this situation, we have a 250 gram mass that we're going to place at the 30 centimeter mark. Now we're going to assume here in this situation that the string is at the 50 centimeter mark, and we're going to place this first mass at the 30 centimeter mark. And we want to know where should we place a 200 gram mass in order to balance this out. So this here, 250 grams, is at the 30 centimeter. Where should we place a 200 gram mass in order to make everything balance? Now, what we want to find here is my 200 grams, which we want to find out how far away we're going to place this. We want things to be in rotational equilibrium. That means we want the torque on the left-hand side from the first mass to balance out the torque on the other side from the second mass. Where remember, the torque is the force times the distance times the sine of the angle. Now, first thing we have to do is we got to get the force of these two masses. And the force we're referring to is the gravitational force, which is mass times gravitational field constant. Now, unfortunately, these masses are in grams, so we're going to have to convert this to kilograms, 0.25 kilograms. And then when we multiply the 0.25 times g, which is 9.81, we get that the force of this one over here comes out to be 2.45 newtons. The mass of this one here is 200 grams, which is the same as 0.2 kilograms. And therefore, to get the force, it is 0.2 times 9.81. And this comes out to then be 1.96 newtons. So now as we make our substitutions, we're going to replace each of these torques with Fd sine of theta. So the force over here is 2.45. My distance, remember the distance is actually the distance from the pivot, which is where the string is, to where the force is located. It is not the 30 centimeters. In this case, it is 20. Now, as long as I keep both sides in centimeters, I'm actually okay. I don't have to make any conversions. And then I have the sine of my angle, and my angle in this situation is 90 degrees because the object makes a 90-degree angle with the force. On the other side, I have my force, which is 1.96. I'm trying to get my distance on the other side, so I leave that as my variable. And then I have the sine of 90, because again, it makes a 90-degree angle with the meter stick. It will always make this 90-degree angle in this lab. Now remember that the sine of 90 is the same as just multiplying by 1. So it's really not doing anything. We could really just type, write down times 1 in this situation. Now I'm going to solve for my distance, and I get a distance of 25 centimeters. Now that is not where I'm going to place this. I can't place it over here at 25 centimeters, and that's going to balance it out. Remember, this distance is the distance from the fulcrum from this pivot point. So it is 25 centimeters further than the 50. That makes this location then 75. So I'll put in 75 centimeters And that's my placement. That's my answer. Now in this next problem here, we have two masses, but it's really the same situation. The first mass is 100 grams, which is the same as 0.1 kilogram. My second mass is 150 grams, which is the same as 0.15 kilograms. And the third mass, I'm trying to find the location of the third mass. That's 250 grams, which is the same as 0.25 kilograms. We want to figure out where to place this in order to balance our system. Now the first one, the 100 grams, is placed at 25 centimeters. That means that it is a distance of 25 centimeters from the fulcrum. My second mass is at the 30 centimeters. That means it's a distance of 20 centimeters from the fulcrum. Now, like I said before, we're going to solve by saying that the torques are equal. This time we have two torques on the left-hand side. So we have torque 1 and torque 2 on the left, causing a counterclockwise rotation. And then torque 3 is on the right-hand side, balancing it out, causing a clockwise rotation. Remember, for each torque, we're going to replace it with FD sine of theta. Now, in all of these situations, our angles are 90 degrees. And the sine of 90 is 1. So to save myself some room, I'm just going to, when I multiply by the sine of 90, I'm really just going to multiply by 1. Now, first thing I have to do is I have to get the forces. Remember, the force is mass times 9.81. So here we have 0.1 times 9.81, which comes out to be 0.981. Here we have 0.15 times 9.81, which comes out to be 1.47. And here the 250 is 0.25 times 9.81, which comes out to be 2.45. So I'm going to replace this torque, number 1, with the force of number 1, 0.981, times the distance of the first one. Well, there's 25 centimeters from the 50. And the sine of 90, which is 1. So I'll just put times 1. For the second torque, I have the force of 1.47. My distance for this force is 20 centimeters from the 50. And again, times the sine of 90, and the sine of 90 is 1. Then my third torque, my force is 2.45. We're trying to find that distance, and again, the sine of 90 comes out to be 1. I solve for that distance, and my distance comes out to be 22 centimeters. Remember, that is 22 centimeters from the 50. So the placement of this one is going to be 50 plus an extra 22, which gets me to 72 centimeters for an answer. Now, there's one last scenario that I want you to look at here, and in the lab there's one more type of situation that you have. And this is if you have your meter stick, what if the string is not at the center? What if the string is not at the 50? And we place a mass over here. And we want to know where to place the second mass. Well, remember that at the 50, the meter stick itself has a gravitational force. So in this situation, if the string is on the left-hand side of the 50, you'll have the torque from the first mass, which will equal the torque from the gravity of the meter stick. You're going to have to figure out the meter stick's gravitational force. Remember, it's the distance always from the string, not the distance from the 50. It's always the distance from the string, plus the torque of the second mass. If the string happens to be on the other side, though, let's say we have our meter stick, and the string is now over here. Again, the gravitational force of the meter stick is at the 50. Here in this situation, you have mass 1 and the gravitational force of the meter stick on the left-hand side. And they would have to balance out the torque of the mass on the right-hand side. So if the string is not at the 50, you have to take into the gravitational force into account. The reason we did not have to do that before was because our distance of the meter stick before was always 0. So even if there is a force of the meter stick here, the distance is 0 and it just simply goes away. So I want you to actually do the calculations. We will test your answers at a different time. So you're gonna solve and make predictions. Where should we place that mass? And then we'll actually get out the equipment, test it out, and see how close you actually are to your estimations.